I know people who are thinking that heart is this romantic organ that shows others your capacity to love, to feel emotions. But you're saying it's a pump.
I'm a pragmatic mechanical engineer.
I can see that. But the big promise of building, a digital twin of the whole human, do you think it's possible?
I think it's definitely challenging, but I would not say it's impossible.
So the good doctor would be also a good physicist or mathematician?
I mean, to use those models, they don't have to be. But the only thing that is needed is the trust that we can do physics.
Karolina, thank you for coming. Would you introduce yourself?
So my name is Karolina Tlałka and I'm a PhD student in Sano Center of Computational Medicine and also on the Medical School of University of Sheffield.
Were you studying and doing your doctorate on the second year, right?
Yes.
So you are working on very specific mechanism that is incorporated in the cardiovascular system. So it allows human to, for example, stand up and not be dizzy, right? So it regulates the blood pressure. And this particular barostimulation is connected to heart, but also to the brain.
Yes, so it's basically the interaction between two models, the model of very simple neural system and cardiovascular system.
You're a physicist, right?
I'm a mechanical engineer.
You're a mechanical engineer.
Yeah.
Working on questions that are more biological, right?
Right.
How come? And what for?
On the basis that human body is basically science.
Right.
And almost all mechanisms of body functioning can be described using physics or chemistry. So my background doesn't really it's not really a threat for the work. It's more like advantage.
Right.
Because if I want to use maths and if I want to use physics, I have to take into account this applied branch of mathematics and physics, and that's basically engineering.
Right. So you see the biological system, cardiovascular system, through numbers, right?
Yes, basically heart is a pump.
Right.
Blood vessels are just components of electrical circuits for me, but for anyone else. So for 3D modelers, they are basically pipes.
Right. So I know people who are thinking that heart is this romantic organ that shows others your capacity to love, to feel emotions. But you're saying it's a pump.
I'm a pragmatic mechanical engineer.
I can see that. But this is for the advantage, right? For the medical advantage that seeing through numbers allows us to create models that then we can put in the computer and have in silico models, right?
Yeah, basically if you turn off the emotions and just focus on facts, you can to precisely describe the physics which is known. So if you can describe the known physics, you can easily understand what's happening inside.
Right. So one outcome of your work would be that we can understand the human body and the systems, biological system better, right?
Yes.
Okay. But the big promise of building, a digital twin of the whole human, do you think it's possible with this current stage of technology and understanding how the body functions, or is it still too complicated to model such a complex emergent system?
I think it's definitely challenging, but I would not say it's impossible in, let's say, 10 or 15 year perspective. we need more resources, we need more computational power, we need more collaboration between the universities, which do sometimes the same thing simultaneously. My PhD actually shows how complicated this problem is, because I am focused on just a coupling between cardiovascular system and nervous system. But there are so many connections in human body, so many systems interacting with each other, influencing each other, that like taking those, I don't know, hundreds of models and putting it into one without the loss of understanding of how it really, for example, makes a decision, that's very challenging.
So let's dive deeper. So in your research, especially in one of the papers, you were trying to figure out how complicated the model should be to represent the functioning of the system, right? Of the cardiovascular system. So would you tell us a little bit more? Why do we need to kind of figure out how complex the models are? What is the trade-off? Mm-hmm. What kind of choices we have, right?
Yeah, so more complex model usually describes physiology in, let's say, more detail. But the trade-off is that we introduce much larger number of model parameters, much more complexity into overall context. While simpler model may not be as detailed, but it can be complicated enough to capture this physiology. So solving modeling problems is always finding a balance between simplicity and between the costs connected with the analysis and with understanding.
So this is this kind of metaphor of map and territory, right? Mm-hmm. You've got a map that is a symbol of certain space, but it's not one-to-one, because if the map is reflecting one-to-one the space, then it becomes territory, right? So you need to kind of find the balance between these trade-offs, right, of the details. And I guess this is something connected also to the capacity of computers handling all the information in, let's say, certain amount of time, right? Because doctors and patients would expect that the information appears on time. And when the models are too complicated, it may cost much more, and it may extend the time of giving the answer, let's say.
Exactly.
How do you define model? Because we're using right now lots of this kind of words that for us capture certain, scientific outlook, right? So the model for you, how would you describe that?
I would say that it's a function, or the set of function, which informed by certain inputs gives us some desired outputs, which can mimic the reality.
Okay, so it's basically like a copy of something or a replica.
Yeah, it's more like digital or mathematical replica of somebody or of something. It also depends if it's personalized or not.
And if we're talking about the cardiovascular system, and now what you said is that making decision how complicated the model should be, then making all the calculations. What are those calculations that are being made using the model?
We can develop a model mathematically. We can describe the reality using functions, but to fully trust the model, we need to understand it. We need to, for example, understand how change of particular parameter can influence model outputs. It also helps us to decide which subset of parameters is so influential that we can use only this subset to further personalize the model, so fit it to specific patient. And those operations are the cost of those operations is highly dependent on how many parameters do we need and how much does a single iteration of a model takes.
But the model simulates the blood flow under certain conditions, right?
Yes.
And through the simulation, we can see if the cardiovascular system of a specific individual is healthy or not healthy, has got certain problems, correct?
Yes.
Okay, and these problems in your case would be the regulation of the blood flow, of the blood pressure.
Exactly.
Okay. And so my question would be like, okay, you simulating something that occurs deeply in the, arteries and all that. How do simulations look like physically? Because you need to base them on real numbers, right? So what's part of the work? How do you capture that in the real people?
Yes, so on my PhD there is no human experiments involved, but usually in orthostatic clinics, for example, because my project is focused on orthostatic stress, so seeing how baroreflex responds in response to changing body position. So, for example, in orthostatic clinics, there are several tests like lower body negative pressure. So, just a patient lying on a bed with legs locked in pressure chamber. We generate negative pressure, which pumps the blood from upper body to legs, and we see how the baroreflex responds. Another example, for example, tilt test. So the patient is lying on the table again, not moving, and the table is tilted with several angles and several velocities. And we check, for example, if someone got dizzy and someone fainted, and we measure blood pressure, heart rate, stroke volume.
Okay, and this is because you can read the system through numbers, right? So that's for me kind of missing picture from how we perceive humans, right? We see each other, especially with artificial intelligence, as a being that is organic, biological, and that kind of makes us human. But we can use math and physics and put ourselves into digital copy, let's say, and then that gives us opportunity, right, to test, I don't know, hopefully in the future, drug use and how certain conditions would impact humans.
Yes, but this approach, of course, doesn't exclude artificial intelligence. It can be a great addition to it. Actually, it helps when artificial intelligence is, let's say, lacking, for example, of explainability.
Yeah, because from what you're saying, I gather that because you know the laws of physics and you've got numerical algorithms, you do not create black box. You create...
Exactly.
Yeah, you create reality that we can see what's going on and we understand it through the math and physics. And when you are building these models, you're thinking about the application in the long run or clinical usefulness of it, understanding that this is a small element and a component of a greater model of human. But what would be your kind of speculation? How would that be useful?
Medical trials usually cost a lot of money and a lot of resources. So, for example, if we have a cohort of 20 patients and we want to simulate this lower body negative pressure experiment, we have to take these 20 people into clinic, measure everything, check also demographical data, etc. And if we want to change one thing, for example, the magnitude of the stimuli, we need to perform all those tests again. While with models which can simulate accurately the physiology under this lower body negative pressure condition, it's just a scope of changing a few parameters in the model. And for example, when we have model which accurately predicts -20 and -30 lower body negative pressure, we can assume that it can predict -40, -50, -60 as well. So we can somehow generate synthetic data from these, let's say, clinical trials without spending any money on performing in vivo experiments again.
And what's the most challenging or difficult thing when you're doing these experiments and pursuing your PhD? What is the most demanding thing?
First thing would be that numerics can be very challenging, and sometimes we face, for example, some stability issues, some computational issues, some problems, for example, with time of computation. That's why we extensively use HPC. It helps us to, let's say, overcome these issues. But yeah, I would say that they are very, very challenging. But also the availability of the data. Medical data is not very common to share open source. So we always, have to look for other collaborations to be able to do something.
And with HPC, would you explain what HPC is and how much GPUs you need to use for simulations?
Yeah, so it depends because firstly, HPC. HPC is high performance computing. So there are huge supercomputers located, for example, here in Krakow, which have much more power than our desktops, and we use it for millions of simulations if we have to quantify the model, for example. So assess the influence of changing parameters, how they influence the output. We have to perform millions of model iterations. For example, one of the analyses that I've made would take something like half a year using a casual desktop, while on HPC it was less than a week.
And you were saying that the problem with the model is that they are unstable?
Yeah, it's more like numerical instability.
Okay, so what does it mean? That it doesn't reflect the real anatomical processes, or?
It does, but sometimes some of parameters that we analyze, that we're taking into account, are highly uncertain. So we are not sure of their particular values in humans because, for example, no one measures it. So we have to assume something. And if you have to assume something, we usually try to, let's say, analyze a large range of variation for this particular parameter. And sometimes we just go into regions where theoretically physics should work, but in practice numerics fails. And that's a common problem with such nonlinear models as mine.
Is it a problem with boundary conditions that you need to estimate, or this is...
Yeah, we can say that.
And what was most surprising in your research?
I think that the most surprising thing was how hard is it to fit the model to particular patient data. Because we estimated that it will take us a month and it took over a year. So that was a little bit surprising and challenging, but we somehow overcome it.
Because that's the big promise of digital twins, the personalization, right? How do you understand personalization in your particular work?
Personalization is fitting the model responds to particular patient data. So, for example, in my case, we have data about patients' arterial pressure, heart rate, and stroke volume. And we first need to find influential parameters, and then using those influential parameters, find such parameterization that captures the physiology of particular person.
Right, so it's like fine-tuning, right, for a specific example. How did it come to this point that, I know that you love physics and math, but why application to medicine?
Yeah, so my first choice of career was actually medicine, but I was lacking very few points on the final exam in the high school. So I've decided that I will go for bioengineering for a year, and then I will go reapply for medicine. But on this bioengineering, I've decided that I prefer engineering than medicine. So I went to this highly engineering, highly physical studies. And then I've decided that, okay, but I spent 3 years of my life just learning biology for the final exam. So maybe I could take it into account somehow in my career. And that's how the opportunity in Sano emerged, and I just took it.
So you combine basically the knowledge, biological knowledge and your interest in medicine with engineering and physics. And what do you think, when you finish PhD, what kind of jobs a person like you would have in mind? Where would that take you?
I would like it to be connected with data science applications, preferably in medtech or in energy sector, because that's what my specialization on master's studies were. I see myself in more like R&D applications.
Right.
So hopefully somewhere where I can be practical, do this, let's say, practical data science, but also do something with research. So go deeper, try to find new methods, try to apply something new.
When we say that AI hallucinates and, gives some things that are not true, what would be kind of the same thing but from the modeling? It wouldn't be hallucination, but what that would be? How would you call it?
For example, in case of AI, the model is as good as data is. In case of physical modeling, the model is as good as mathematical equations for physics. So, for example, if we have some regions in the body, for example, that are not well investigated, this physics-based model can not be so accurate.
Because it's based on assumptions that might not be true.
Exactly.
What's the connection between heart and brain?
Basically, heart is actually self-reliable, let's say, like in basic functioning. But when, for example, something changed, like, for example, pressure drops, we have receptors located in carotid sinus aortic arch, which can sense those changes of pressure, and they can transmit the signal to the brain, and the brain will respond to those changes, so the homeostasis would be preserved. So, for example, brain can speed up the heart, slow it down, it can stretch your blood vessels, it can change the contractility of the heart.
You're more a person who you would use the term brain more often than mind?
Yes.
Because, heart can survive by itself, right?
Yeah, that's why I told at the beginning that it's kind of independent, but the brain
No.
helps it. The brain helps the heart to, maintain the balance.
Is there any part of my cardiovascular system that reacts when the blood pressure needs to change? And how does communication, heart, brain, looks like?
There are receptors located in aorta and in carotid sinus.
So somewhere here.
Somewhere here and somewhere here.
On the
Yeah.
level of my neck.
And
Okay.
yeah, and then they can sense the changes of pressure. Actually, they just transmit the information to the brain all the time. But when this information is changed, is perturbed, the brain catches that and generates response which has to counteract those changes.
What would be the closest metaphor for this kind of adaptive complex system? Because I think that the pump doesn't hold the whole truth.
I mean, when it comes to the regulation problem, the easiest way would be to just say temperature sensor.
So thermostat, like
Yeah, you have thermostat. When the temperature in the room drops, it just turn on the heating. So the temperature went back to the, let's say, optimal level.
So this is a classical cybernetic example of thermostat that not only reads the temperature but can adjust, right?
Exactly.
So is this cybernetics that you're doing?
Yeah, I think that Professor Ryszard Tadeusiewicz would agree.
Yes, he would. I had a pleasure meeting him and chatting to him. He uses lots of different metaphors and that are kind of holding very complicated ideas in the picture that allows you to penetrate this kind of complex systems a little bit more. So do you, I don't know if you agree, but do you see that, biology can benefit from so many different sciences, not only artificial intelligence, but also math and physics to understand human systems, not only disease, but human system better, right? And to maintain it maybe longer in health, for example.
Of course, I would say that in terms of explainability, actually those physics-based models are much more beneficial than artificial intelligence.
So the good doctor would be also a good physicist or mathematician?
I mean, to use those models, they don't have to be. But the only thing that is needed is the trust that we can do physics.
Right. And then they can use the tools because the trust appears. So Karolina, you like films. What are you recommending in terms of, entertainment, coming home, watching something?
I would say Dune definitely.
Dune.
Yeah, all the parts with all the directors, because there are several. There's this iconic Lynch version as well.
So you've read the book before the film or after?
I've read the book after, I must admit.
Because I heard that people who read the book, they were like, oh, the book is too complex to just put it in the movie. I haven't read the book, so I actually appreciate the movies. So K-pop Demon Hunters, not your genre?
Definitely not.
I know in the team somebody who is watching that, so that will be in the next episode. So thank you very much for today. It was a pleasure talking to you, and yeah, it was great.